Hey everybody, welcome to chapter 3.2, where we are talking about trickery, quantitative variables, and distribution shape. Let's start off with some review. What type of graph or chart is appropriate for categorical variables? That's going to be D, both bar graphs and pie charts. And indeed, you can actually show the same data in two different ways using both of those charts and graphs at the same time if you want to. Most people in psychology produce bar graphs by far and away. Pie charts can be useful as visualization aids for specific kinds of data where you're mostly trying to just show percentages of different kinds of categories. Bar graphs, on the other hand, are useful in a much broader array of situations. We talked about things that could be misleading or wrong with pie charts, so let's do it with bar graphs as well. So what is a little bit misleading here? You've got a bar graph, a simple bar graph that looks like it's measuring customer satisfaction with, let's say, four made-up restaurants. You got the Rusty Spoon, Pub Subs, Patricia's, and Lefties. These are all, the thing is, we assume that the scale is from 0 to 100 customer satisfaction ratings. And the problem is, whoever made this graph actually cut out most of the graph, right? Because if it's on a scale of 0 to 100, we're only seeing the scale from 90 and above. And so somebody who was on the payroll of Lefties and wanted to show you or suggest to you that Lefties has much, much higher customer satisfaction ratings than other local restaurants, they might try to dupe you by showing you what's called a truncated graph. And so it's truncating the y-axis. Now, it's not wrong in that like the numbers are still correct, and if you zoom in, so to speak, on that area of the graph, that is what it looks like, but it's not the full story. So if you actually zoom out and use a 0 to 100 scale, y-axis for customer satisfaction, you can see that these bars are like basically not different at all, even though this is the exact same data. So just something to be wise to. So let's talk about the types of graphs that you might want to use for quantitative data. A common type of chart or graph, especially if you have an independent variable that is continuous, like time or age or something like that, you put that on the x-axis. So we have, in this instance, recycling rate versus year. So year is going to be in this case, it's interval because years, there's no real true 0 point of years. We'll talk about some exceptions to that in a minute. But basically, in a line graph, you look at separate points, and you're going to, if you were creating this by hand, you would say, okay, at what point on the x-axis am I wanting to put a dot? So let's say 2008. And then I would look at some chart, some table that shows me in 2008, what was the recycling rate, let's say, of Columbia. I just made that up. I don't know what city this is for, but let's say it's 25%. And so then I go from 2008, and then I start climbing upwards until I get to the y-axis of 25% and put a little dot there, right? And you just connect the dots after you put all your dots down, and it creates this beautiful line graph. Now, so far I've shown you line graphs that always have time as the independent variable, meaning they're plotted on the x-axis. But you could put anything on the x-axis as long as it's in a line graph, as long as it's some kind of numeric value that as it increases, you're getting more of that thing. And so here's drug concentration, for example, on the x-axis, and then the biological effect of that drug is on the y-axis. The final type of graph we're going to be talking about is a scatter plot. And this is when you have two variables, an x variable and a y variable, let's call them, that are both on a numeric scale. And you just want to see how are these two things related. And so each dot in a scatter plot represents a single person and the corresponding amount of the x variable they have and the y variable they have. So let's just use this scatter plot, which is the level of intoxication from alcohol that somebody is at based on a 1 to 7 scale, and how long they can balance on one leg. And so you can see that, let's go all the way to the right. One person had a level of intoxication of 7, which for them corresponded to an amount of balance, time they could balance on one foot of about 25 seconds. Okay, so that one single dot represents one single participant's data for both of those variables, right? Hopefully that makes sense. Then you can like put on a trend line and see overall, like as the level of one of these variables increases, let's say the level of intoxication, what happens to the other variable? Does it tend to increase? Does it tend to decrease? In this case, it's decreasing. So as the level of intoxication goes up, balance tends to decrease, or amount of time you're able to balance tends to decrease. And we'll talk about this more when we get to correlations. The next type of graph you could use for quantitative data, like ratio data or interval data, we've already covered, right? This is the histogram. And again, on the x-axis is just the possible values of, say, a scale, or the likely values, in this instance, of number of cups of coffee people drink in one single day. And then on the y-axis is just the frequency. That's how many of the participants in your sample scored that score or drank that number of cups of coffee. And so you can see I made this data up. This doesn't have anything to do with the previous smaller table of cups of coffee drinking. I just added a bunch of random participants, and it looks like, oh, cool, in this particular sample, 15 people drank 1 cup of coffee during the day. A bit less than 10 people, let's say 8 people maybe, drank 2 cups of coffee a day. And then it looks like one person is a little bit of an outlier, and they drank 8 cups of coffee in one day. All right, now let's talk about something that is actually very, very important to consider. That is the shape of distributions, frequency distributions, or we'll get to probability distributions in a bit. It matters because the shape of a distribution, which would be like the histogram on the previous slide, will tell you which measures of central tendency, mean, median, or mode, that you should be using. And it also has implications for certain assumptions when we're using inferential statistics like t-tests and ANOVA and correlations and all those kinds of things, okay? So the shape of the distribution is something we actually want to pay attention to. Now, frequency distribution graphs, histograms or bar graphs, right? They make it easy to see the shape of the distribution. That's really nice. It tells you, generally speaking, where do a lot of the participants line up when they, how do they score on an IQ test? How do they, what is most of their nationality or age or ethnicity or gender or something like that, right? Now, the shape of the distribution, that's just, again, the shape of a frequency distribution of a set of numbers. It can take on basically infinite amounts of forms, depending on how many numbers there are, how many participants there are, and the possible amounts of variation within that single variable that you're looking at. And again, this really affects how the researcher analyzes the data in terms of which descriptive statistics they want to use and which inferential statistics are going to be valid for that data. One potential shape a distribution could take would be a symmetrical distribution. And you can see that the center of the distribution is the highest point. That represents the mean, median, and mode. In this case, we'll talk more about this in Measures of Central Tendency chapter. And so you get this nice curve that is a mirror image of itself from left to right. And an example of the asymmetrical distribution is the normal distribution, which we'll talk about later on as well. However, there are a lot of distributions that could be skewed, and that means that they're not symmetrical. It means that the highest frequency or count of some rating or some measurement is on either going to be towards the left side of the graph or towards the right side of the graph, and so that's going to create a skew where it's not even and symmetrical on both sides. You can have positive skew, that's also sometimes called right skew. You can have negative skew, which is sometimes called left skew, and I always know that or remember that by basically where the tail of the distribution is, where it gets stretched out, either to the left or to the right. And so if the tail gets stretched out to the right, it's positive skew. If the tail gets stretched out to the left, it's negative skew. And positive skew means that there are a lot of scores bunched up towards the lower end. That's why it's higher. And that's why the distribution is higher at that end. Versus there's going to be infrequent scores at the high end of the x-axis, which produces that drawn out tail that stretches onto the right side. And when researchers see skewed data, a lot of times that can mess with certain assumptions of various types of testing when we do inferential statistics. So if you have a really highly skewed distribution for one particular variable, let's say that you're measuring IQ, and like almost everyone in your sample has a super high IQ, and for whatever reason you have just very, very few people with low IQs. Well, that's going to generate a really skewed sample, a really skewed distribution that might look something like this, where it's like, well, there's a bunch of scores on the right side, on the high side of that measurement, and not very many scores on the left side, and that's producing skew. And so I would have to maybe take care of that by doing what's called a transformation. We won't talk about that in this class, that's more graduate level stuff, but you might want to remember some values of skewness that I could ask on a test or quiz, because again, a lot of skew in a distribution can violate some assumptions of different inferential statistics that we can talk about later on. So what I would know for you is values of skew that are close to 0 mean that it's a more symmetrical distribution. Because yeah, the lack of skew means it would be symmetrical. If skew is between -0.5 and 0.5, then the distribution is approximately symmetrical. Okay, so if it's close to 0, then it's approximately symmetric. But if the skew is outside of those values, so if it's between -1 and -0.5, or between 0.5 and 1, then the distribution is moderately skewed. If the skewness is less than -1 or greater than +1, then the distribution is highly skewed. And so you can see in this example here, the skewness is -1.60, -1.60. So that means that this distribution is left skewed, it's negatively skewed, and it means that it is highly negatively skewed because it's less than -1. -1.60 is less than -1. So on a quiz or an exam or something, I could give you a value for skewness, let's say +0.40. And you would have to tell me, okay, does that correspond to a left skew or a right skew? And is it approximately symmetrical? Is it moderately skewed, or is it highly skewed? And sometimes I just can't resist a corny little joke that you can take a look at for yourself. All right, what type of graph is most appropriate for quantitative or numeric independent variables? So we're talking about things like interval and ratio variables. The correct answer is E. Both line graphs and histograms. Depends on what kind of data, what kind of variable you're looking at. If you want to do a frequency distribution and you're looking at the number of participants, so the frequency of participants that score on, let's say, a 1 to 5 scale, each of those numbers on that scale, or 1 to 7 scale, 1 to 9 scale, you're probably going to be talking about a histogram. Line graphs are particularly good for things like time or maybe age or something like that. All right, that's it for this chapter. We'll see you in the next one.